All right, so you should have a graph of position time that looks like this curve. And next you would want to, in Logger Pro, you would want to go Analyze Model. And as you can see, it's definitely not a straight line. As the object sped up, the slope of the position time graph gets steeper to show that it's speeding up. So neither of these two equations will work. The first curved equation is called a quadratic, and we're going to try to fit that one. And if I can basically change my A, B, and C over here. And so I'm going to change my A until the curve looks like it's about right, maybe the right shape, maybe a little bit down, maybe about like that. I'm going to make these 0 first to begin with, and I'm going to get this one as close as I can. That looks pretty good. Then I'm going to move it down, maybe move this one a little, and that looks pretty good. So now I'll hit OK, and it looks like I have a nice graph. And this curve is a very close curve fit. It's a best fit curve of my data. And you wonder, well, what does this mean, right? Well, if I take any object that's moving, in the last unit, here, I'll just make it a star. In the last unit, if I made, for every second that goes by, our object would travel the same distance. So if this was a number line, if there's a number line here, right, every second, your battery-powered car traveled the same distance. One nice way of showing this is to draw velocity arrows. This is a velocity arrow right here. Okay, I'll call it V for velocity. And I'll move it so it looks nice. And now group these together, right? And you ask yourself, well, is the velocity changing? And clearly it isn't. So if I clone these, here's this moment in time. Here's this moment in time later. Here's this moment in time later. Maybe I'll do a couple more. 2 more. Here's this moment in time. Here's this moment in time. So if I draw this correctly, what I'd be showing is that none of these velocity arrows actually change length. They're all the same exact length. And that shows that the velocity didn't change. This is why we called the motion in the previous unit, we called it constant velocity motion. Okay? And if you draw like a number line, this is position measured in meters, okay? X meters, right? Okay? At different moments in time, our object would be at different positions along this number line. For example, in the first moment, the tail of the arrow shows where the object's at, so our objects might be at 0. And then at the next moment, it could be at some greater position, maybe 2 meters. And then the next second, it might be 3 meters. And then 4 meters. And then 6 meters. And then like 8 meters. So that was constant velocity motion, right? So I'll make this 0. And then I'll copy this over. And I'll move it over here. And I'll make that like 2. I'll make this one 4. And I'll make this one 6. And I'll make this one 8. And I'll make this one 10. Okay? So that's 10. This one's like 8, let's say. And this one over here is like 6. And this one might have been 4. And this one might have been 2. Okay? That would be constant velocity motion. All right? On the other hand, the motion we're studying now, you're going to make hearts. Yeah, hearts are cool. All right? So now we don't have the same situation at all. We've got an object that's actually speeding up every second. So whatever distance our object goes in the first second, it's going to go a lot farther in the next second, okay? It's going to go like, for example, if the heart moved this far in 1 second, right? If it moved from there to there, from here to there in the first second, just hypothetically speaking, right? Then in the next second, it's going to go like 1, 2, whoops, didn't want to do that. It's going to do 1, 2, 3. So it's going to go much further. It's going to go 3 times the distance in that second. This is why in your equations you have a square. You have an equation with a square in it because, let's see here. If this is 0, right there, let me make another heart. So the heart actually, the object is actually like over here now. And in the first second, let's say it went, just hypothetically speaking, let's say that it went this far. That would be 1. The next second, it's going to go like even farther, okay? So in the next second, it's going to make it all the way to 4. And there, those numbers should kind of look familiar. That's perfect square. And then in the next second, see if I can do this. It'll go 5. Whoops, I didn't want to do that. Try that again. 4, 5, 6, 7, 8, 9. So it'll actually get to 9. There's a cool pattern here. Basically, in the first second, it goes X distance. In the next second, it's going to go like from 1 to 2 seconds. It was 0 to 1 second, it might go like X distance. But from 1 to 2 seconds, it'll go 3 times farther. In the next second, it's going to go 5 times further. In the next second, it goes 7 times further. This pattern is just following the odd numbers. And when you add the odd numbers, you get the perfect squares. It's like kind of beautiful. So see if you can figure out where the heart's going to be after the next second. This is 0, 1, 2, 3. At the 4th second, let's say, where is this object going to be? I could just draw some marks down. 10, 11, 12. Whoops, didn't want to do that. 12, 13. Whoops. 13. Oh no, come on. Here, I'll just do it this way. And then this guy is 13. 14. Okay. Almost there. 9, 10, 11, 12, 13, 14, 15, one more. Okay. So that would be 16 there. So let's copy this over. And this will be 16. So I'm just trying to give you a sense of the pattern that's going on. you can see from the hearts, in the first second, the heart goes 1 meter. The next second, the heart goes from 1 to 4, which is 3 meters. And the next second, the heart goes from 4 to 9, which is 5 meters. In the next second, the heart goes from 9 to 16, which is 7 meters. And then if I look at the positions go up with the square of time. Because in the first second, I go 1 meter, but after 2 seconds, I'm at 4 meters. After 3 seconds, I'm at 9 meters. After 4 seconds, I'm at 16 meters. So that's why in your equation it has a t squared in it. It's this square relationship. And then if I want to draw a motion map, what I would do, I could just copy this one down here, right? And then this might be the speed after 1 second. And then, so what you'll see on this motion map below is the arrows actually have to get longer. These are called motion maps where we use velocity vectors to represent the velocity as this thing speeds up. So this is a motion map for something that's speeding up. And you can see the arrows get longer to show you that the object's speeding up. The arrow length is the velocity, whereas the direction of the arrow is just the direction you're moving. So I thought I would use motion maps to kind of show you what was going on with the overall pattern when you're changing your speed, when you're speeding up, compared to the last unit when you had something moving with a constant velocity. I just want to highlight the differences and kind of give you a sense of it. Again, you'll notice the distances traveled go up with the odd numbers each second, and then the positions actually go up with the square of time. Whereas with constant velocity, position is directly proportional to time, so the positions are directly proportional to the time that the object is moving. Anyway, hope that helps, and have a good day.